We're looking at organic chemistry, and we're specifically looking at organic compounds acting as acids and organic synthesis. So our learning intention is to explore organic chemistry reactions, including their mechanisms and the chemistry behind them. So first, let's look at organic compounds that act as acids. So the first thing we'll do is we'll look at a reaction between our alcohols and sodium. So when sodium metal is added to ethanol, hydrogen gas is given off and sodium ethoxide is formed. And this here is our reaction for it. We can see that the sodium metal reacts with the ethanol to produce sodium ethoxide and hydrogen gas. And we can clearly see here that the hydrogen that is on our alcohol is being replaced by a sodium. So the alcohol, which is ethanol here, is behaving as an acid because it is losing a proton, i.e. it is a proton donor. And this can mainly happen due to the polarity of the OH bond, and that makes it easier for the hydrogen atom to break off. Now, it is worth noting that sodium is far less reactive with ethanol than it is with water. However, alcohols are much weaker acids than water, so they're so weak that they do not react with bases. They only act as acids in the presence of reactive metals, and we know that sodium is a reactive metal because it is in group 1 of the periodic table. And that's as far as we need to go when we're looking at alcohols acting as acids. So the next thing we'll look at is we'll look at the carboxylic acid group acting as acids. So carboxylic acids have the ability to act as acids for 2 reasons. And the first reason is something called the inductive effect. So the carbon atom of a carbonyl group, they tend to have a slightly positive charge. So they tend to attract electrons. And this slightly positive charge comes from the highly electronegative oxygen that is attached. So the carbon pulling electrons towards itself is called the inductive effect. So basically, the carbonyl has the effect of drawing electrons away from the OH group, as we can see here. And as a result, this helps with the ionization of the hydrogen atom in the OH bond. So that basically makes it easier for the carboxylic acid to donate this proton. Well, the second reason that allows carboxylic acids to act as acids is the stability of the carboxylate ion that can be formed. So when a carboxyl group loses a proton, it forms a carboxylate ion, and a carboxylate ion has a negative charge. And we'll see the structure of the carboxylate in just a moment. But from X-ray studies, it was found that the 2 carbon-oxygen bonds in the carboxylate ion are actually of equal length, meaning that the negative charge on the oxygen must be delocalized over 3 atoms. So here we see the term delocalized, where we've met it already with our benzene. So this delocalization allowed for a new structure called a resonance structure to be formed. And here we can see the negative charge is on this oxygen in the left-hand side, and it's on this oxygen in the right-hand side. But what we actually have is we have a resonance structure like here in the middle, where the minus charge of the oxygen is spread over 3 atoms. It's spread over the oxygen, the carbon, and the other oxygen. So the fact that the carboxylate ion is so stable means that the carboxylic acids can lose protons readily. So the last thing that we're going to do in this video is we're going to look at organic synthesis. So to begin, it's good to do a definition. So our definition for organic synthesis is a process of making organic compounds from simpler starting materials. And in organic synthesis, you must plan the steps, usually a number of them, and then design the experiment. And the new molecule that's made in organic synthesis is called the target molecule. Often in organic synthesis, an intermediate is formed, and this is usually before the final compound is obtained. It's important to know that organic synthesis involves bond breaking and bond making. And two useful compounds that are synthesized by chemists are aspirin, which is here on the left, and paracetamol, which is here on the right. So to show organic synthesis, we are going to discuss the synthesis of PVC, which is polyvinyl chloride. So the first step of synthesis of PVC is ethene reacting with chlorine to form 1,2-dichloroethane, and that is our first intermediate in the synthesis of PVC. So as you can see here, the ethene reacts with the chlorine to form the 1,2-dichloroethane. So our double bond is broken and the two chlorines are attached on to the carbons as a result. So step 2 is where the 1,2-dichloroethane is subjected to a process called thermal cracking. And thermal cracking removes hydrogen chloride from this molecule, forming chloroethene, which is our second intermediate, as we can see here. The final step of our organic synthesis of PVC is the polymerization of our chloroethene. And we've already met polymerization, so that is where monomers react together to produce a polymer. And the polymer that is produced from polymerization of chloroethene is PVC, which is polyvinyl chloride. So that's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.